Bethany Roten is our secretary. She's also out of the country right now. And we've also got several trustees with this organization. Brad Haney, Jason Hissong. Why am I drawing a blank? We've got Charles Cunningham, and then Ben Roten is currently with Bethany out of the country on vacation. Couple things to just discuss with everybody tonight. Our officers and trustees just concluded our board meeting, and we had two main accomplishments to report out on. Number one, we just approved our budget for 2026. We will include a copy of what that looks like in the March edition of the Prime Focus. Additionally, we're also working to refine an equipment loan-out policy for the club. I think that we're going to have that policy approved at our March board meeting and pretty much effective at our March meeting. One thing that you guys will probably see is a list of our club inventory. Once we get that updated, we'll include that in the Prime Focus edition, just so folks know what they've got kind of at their disposal to borrow from the club. Two things that I'm just looking in general from club membership for some assistance with. We're looking for a new property manager or equipment coordinator, somebody whose role will be to coordinate the loaning and receiving back of the equipment when we do loan that out. So if your life's ambition has been to be a property manager or an equipment coordinator for an astronomy club, please see me after this meeting and I will help you fulfill that dream. I don't know about you, but the only thing more exciting to me than club equipment is club constitution and bylaws. I'm trying to keep a straight face. Help me out here, guys. So it has been a little while since our constitution and bylaws were last updated. And when we were doing a review of those recently, there's some things in there that probably need updated or changed just based on the needs of our club or how we've historically operated. So with that, we would like to try to establish a constitution and bylaws committee to sit down, review the bylaws, and make recommendations for changes that might benefit the club so that we can decide on the best route forward there. So with that, we're also looking for somebody in the club who's interested in serving as a Constitution and Bylaws Committee chair. So if that has been your life's ambition, or if you love nothing more than reading Constitution and Bylaws for clubs or civic groups or whatever, also see me after the meeting, and I can give you a rundown of kind of what our Constitution's like and what that process might entail. So with all that being said, while you guys navigate your excitement, I'd like to turn it over to Don Stevens, our Perkins Observatory Director, for his report. If I can pull this up. Here you go, sir. And the microphone.
All right. Greetings, I'm your host for the meeting here, Don Stevens, Director. We've resumed our Friday night public programs. They started at 8 p.m. They happen every Friday, rain, snow, or shine. And the main thing I need is volunteers to help with those programs, in particular things like telescopes, to show the folks that come to the program, show them things and talk a bit about them and share your love of the hobby with them as well. You don't have to be an expert. You know, you don't even have to have your own telescope. We've got a couple telescopes that we can set out there for you to use, and we'll pair you with someone that's more experienced as well to help you find things to point out in the sky and that. So please, if you got nothing you want or something you want to do on a Friday night, just come on out and join the program and help us out. It's appreciated. So it'd be nice to have help out there with the parking and stuff like that, or just be around the observatory, answer people's questions and things like that. So there's all kinds of ways that you can contribute and help with the programs. So again, those are Friday nights. This time of year they start at 8 p.m. Usually folks start showing up around 7 p.m. for that. And I typically will post on the email list, particularly on nights that I need help. And so watch for that. And if you can help, please come to the program and give me a hand. Yes?
I have a question. You mentioned parking. Given snow and soft ground and everything, how are people parking?
Well, right now, the program size are limited. I'm limiting to typically 20 to 30 guests. because of the fact, we're down to one single occupancy restroom. So not typically a whole lot of cars out there for that reason. So there's room in the parking lot for the volunteers to park as well. Later on, when I'm able to expand again back to some of our original capacity, parking does become a little bit more challenging. Typically, we park people, along the driveway and things like that. It can be a little bit of a problem with the snow and such. But we do, unfortunately, the best we can. The parking lot is what it is. And, if someone's got a couple $1 million that can donate to me to expand the parking lot, I'd definitely make use of that. It'd be appreciated. Any way you can help out is appreciated. Also, along the lines about the restrooms and that, I'm getting a little bit of movement finally from the administration on getting that work hopefully done here. They've approved me being able to access the excess funds that I have in the account to do some of this work. Now it's just going to come down to being able to get the contractors in here and things like that. And unfortunately, there's a lot of red tape involved with those things as well. Do bear with us. I am trying to get this stuff done, get those restrooms back open again and things like that. So that way there's not lines out there waiting to get a chance to go to the restroom and such. So I appreciate your patience on that. All right. Any other questions or anything for? Okay.
All right, none. Thanks, Don. We'll go ahead and turn it over to Brad Haney for the John Glenn Astronomy Park Director's Report.
Thank you. Howdy, gang. Just to let you know, the public programs at the John Glenn Astronomy Park started back up on March 6th. That's a Friday. That's the first full weekend in March. This upcoming Saturday, the following Saturday, we will be having a thank you party for anyone who has volunteered at the Astronomy Park. I see a number of people who have volunteered. That is at 4:30 at the lodge. After that, if it happens to be clear, currently the long-term forecast does not look promising. However, if that changes, it's Ohio, it will very likely change. I'll open up the observatory afterward for, an unofficial observing session, just for those volunteers to do what they will and enjoy the night sky. CAS in general is also invited. So if you guys want to come down, especially if you've never been down to the Astronomy Park, if you want to come down that evening at sundown, if it happens to be clear, we will be opening up the observatory. So that's pretty much it. So thanks.
Thank you very much, Brad. Next, we'll go ahead and turn it over to Joe for the outreach and membership report.
Yes.
Outreach and guests. Sorry.
We have some guests today, Lena and Mott. They were bold enough to sit in the second to the front row. So I'd like to welcome Lena and Mott. Welcome. And then I have an invitation that's been extended to the club and its membership and their friends from the Boundless Journeys in Vermont, who would like to invite us, if we are interested, to join them for a trip to Spain for the solar eclipse over Spain, August 9 to 16 of this year. If you are interested, see me at the end of the club today, or give me an email. And they are offering us a discount of $500 to attend that program if we'd like. So if you're interested in going to the solar eclipse in Spain in August of this year, see me. The $500 offer expires on March 6th, so you have to act rather quickly.
That's $500 off.
$500 off.
Right.
Yeah. Yeah, thank you. It's $500 discount. There's still the, whatever they're charging us for the program, which I would think would be substantial for a week in Spain. But anyway, if you are interested, give me an email or see me after the club meeting, and we can get you signed up.
Thank you very much, as always, Joe. As many of you guys know, we have a couple of kind of interest groups or societies within the umbrella of Columbus Astronomical Society. One of those is the Columbus Astronomical Society's Imaging Society, CASIS. Isaac Cruz leads that. He's out of the country usually, or out of the state this time of year due to the cold weather. And with that being said, he does have a CASIS update. Mark Noldemer, and I apologize if I mispronounced that, is going to lead the first CASIS meeting of 2026 on Saturday, February 21st at 1 p.m. here at Perkins. They plan to have the CASIS meetings in March. Let me make sure I'm reading this correctly. We plan to have the CASIS meeting in March, the Pixon site workshop in April, and then they'll resume normal meetings from May onwards, the third Saturday of the month. The highly anticipated Pixon site workshop is still planned for April, specifically Friday, April 17th through Sunday, April 19th. The workshops will begin here at Perkins Observatory at noon, and fine details and sample data will be provided on or about the March CASIS meeting, so sometime mid to late next month. The cost of the workshop is going to be $225 per person, and that will include all 3 days of instruction. So that's all I have regarding the CASIS update. So it's exciting that that'll restart next month or next week. If you're interested in imaging, it's well worth your time. Another thing we've recently started is a Columbus Astronomical Society observing group, and Charles has taken the lead on that, and he's got a couple words about the March program we've got in mind.
Yeah.
There you go, sir.
Thank you. So anyway, it's something I've been wanting to do for quite a while, and that is have official club observing outside of the regular meeting night, which has been a little hard to do. But in March, there's going to be Messier Marathon, yeah, where you try to spot all the Messier objects in one night, which is a considerable feat, but and if you want to stay up most of the night. But anyway, we're going to start there. We're planning on having it down at J-Gap, and good luck to you all, you know. So that's going to be our first event, but then we're going to try to organize some other more local events in the future, try opportunities for people to get their telescopes out and outside their backyard where the street lights aren't, someplace where street lights aren't shining. So we'll see how it goes, and if you have any ideas for an event or something, just send me an email. Yeah.
Thank you very much, Charles. And that Messier Marathon is tentatively scheduled for March 21st. Of course, weather provided, and here in Ohio, it's anybody's guess what that's going to be like. Hopefully not a foot of snow and 20 degrees below zero. The next thing I just want to bring up is we're also looking at trying to create a citizen science special interest group under the CAS umbrella. We're still working out some of the details, but one of the things that we're looking to do maybe as a project for 2026 is trying to assess sky brightness around different parts of central Ohio where we might do typical observing. So we're looking at starting a group to look into how we can take that on as a project, go out and measure and take some observations of sky brightness and somehow quantify that data so that we can see where the good spots are and where the not so good spots are, and even be able to put some data to that. So hopefully next month at the March meeting I'll actually have some formal logistics on a meeting, but if you are interested in citizen science and have some strong opinions on it, please see me after the meeting. I'd love to kind of hear your thoughts so we can get this off the ground. Moving further through our agenda here, we've talked about that, and we're now to the presentation part. So tonight we're excited to have one of our trustees, Jason Hissong, with us to talk about some more of his work with the SeeStars, this time talking about stellar spectroscopy. I think I pronounced that correctly. When I first heard about the SeeStar telescopes, I wasn't particularly excited about them, and then Jason did a presentation last year on them, and it was pretty eye-opening. And if you've never played with one of the SeeStars before, take an opportunity to do so. They're not particularly expensive, but they bring along some great capabilities for just astrophotography, but there's also some scientific components to that. So with that, we'll turn it over to Jason.
All right, I'm going to start turning the lights out. Now you guys can fall asleep, as I'm sure this will be boring. Anyways, good evening, everyone. For those of you who are new here, I'm Jason Hissong. I've been a member of the Columbus Astronomical Society now since 1999. I can't believe it's been that long. I've done a lot of stuff in this hobby. I've been doing imaging or astroimaging for a long time. I've built telescopes. I've ground my own mirrors. So I've done a lot of stuff. But ever since I got started in astronomy, I found that smart telescopes is probably one of the most revolutionary things in amateur astronomy. So, excuse me, I want to start a series of presentations to explain some of the scientific aspects of what you can do using a smart telescope. Now, my telescope I'm going to be using is the SeeStar, but some of these concepts can be applied to other smart telescopes. So for those who have like a Dwarf 3 or a Dwarf 2, a Vionis, whatever, some of the information I'm going to provide you will allow you to do that. So the first of this series, we're going to be capturing stellar spectra. And then we're going to be using inexpensive items, and that's an important thing. So you won't be able to do like some really in-depth scientific things with spectroscopy on the SeeStar, but it is a good activity with students, with the community, yourself or as a group, because there are some interesting things that you can do. Let's talk about what is spectroscopy. So, in my opinion, one of the most important events in astronomy and science was the invention of the spectroscope. Of course, besides the invention of the telescope, that was pretty important too. Spectroscopy, or a spectroscope, or the study of the spectra of stars, has really shown us that the stuff out in the universe for a long time, people thought that the stars were like perfection, or it was free from corruption and all that kind of stuff. We had a low self-opinion of ourselves. But with spectroscopy, we were able to show that what's out there millions of light years away is made up of the same ingredients that we have here on Earth. Spectroscopy broke through long-held beliefs about the universe and enabled us mere humans to understand how the heavens work. Now, before we get into how we can use our humble smart telescopes, or SeeStars, to do some rudimentary spectroscopy, I want to talk about what spectroscopy is. And I want to go through a history of how we started using spectroscopy to help us understand the heavens. So, what is spectroscopy? According to my notes, spectroscopy is the scientific study of how electromagnetic radiation interacts with matter. By splitting light into its components' wavelengths to create a spectrum, scientists can identify chemical composition, temperature, density, and motion of objects, ranging from microscopic molecules to distant galaxies. So let's talk about some core principles. So every atom and molecule has a unique spectral fingerprint. It can emit, when excited, or absorb light, and that fingerprint allows us to see what that substance or sample is. So there's two types of spectroscopy. well, two types of things you identify in spectroscopy. So up there you see an example of a continuous spectrum. It's like, think of the rainbow. We have emission lines. Emission lines happen when that sample is excited by like heat or ultraviolet radiation or electricity, etc. Every element has a unique signature, and we'll look at some of those in a second. Conversely, we have something that are called absorption lines. So if you have a gas in front of something that's emitting light, like our sun, you will see those same fingerprints as absorption lines when they're not excited. They're blocking light at a particular frequency. Here's an example of some common elements that you're probably familiar with. Hydrogen. I'm sure a lot of us heard of hydrogen. Helium, oxygen, right here. And you'll see each one has these characteristic lines. And it's always consistent, right? When you excite an atom of hydrogen, that atom will emit, or those electrons, and I'll explain how this works. Those electrons jump into a high energy level in the atom, and when it falls back down, it emits a photon of light at a specific frequency. And you'll have it at different frequencies. So, for example, sodium. This is very common. Have you ever noticed when you look out in the light pollution, it's kind of got that yellowish, orangish haze? It's mostly because of this line right here. They call that the sodium line. Neon, I'm sure most of us have heard of neon signs, has a lot of these different lines in it. I didn't realize there were a lot of those lines. So each element, also molecules, when they're excited, where something causes the electrons to jump into an outer energy level, and when it loses that energy, it falls back down and it emits a photon of light at a specific frequency. So, I thought this was really neat. Every element in the periodic table has that spectral fingerprint. There's a company out there, they're called Field Tested Systems. You can buy this, and I plan to get one. You could buy this as a poster where it shows you all of the spectral lines for each element. So it's actually kind of interesting. They can simulate this because they understand how this works from a quantum level. They can simulate even these synthetic elements that we have only had for a microsecond or a nanosecond in existence. Because they understand how it's set up, they can predict the spectrum. I thought that was kind of interesting. All right. I'm a history nerd. So in preparation for this talk, I did a lot of research and how we got here. I'm sure you guys know this person, right? He's the one that created the Dark Side of the Moon album. Yeah. I say that to keep you guys awake. So anyways, Sir Isaac Newton. So in a paper in 1692, Newton illustrated that sunlight can be broken into many different colors using a simple prism, which is based on all work that's on color and color vision. So one of the things, he discovered how the information from the sun, when it's broken up into different colors. So he's like, sunlight is broken up into many different colors. A little later, in 1802, this guy right here, his name is William Hyde Wollaston. He noticed dark gaps in the solar spectrum, but thought they were just merely boundaries between the colors. 12 years later, this guy, and he's pretty famous now, his name is Joseph von Fraunhofer. He invented the spectroscope. Now, and he began to document these lines that he noticed in the solar spectrum. Today they're still referred to as Fraunhofer lines. He also didn't know what they represented, but he documented it and provided a map for others to look into. Oop, go back one. So by the mid-19th century, Gustav Kirchhoff and Robert Bunsen, yes, that Robert Bunsen that invented the Bunsen burner, made a breakthrough discovery that these lines represented by chemical elements in the sun's atmosphere absorbing specific wavelengths of light. They compared the spectrum, or the spectral signatures of various elements. Remember I was talking about each element has a spectral signature. And they found that they matched some of those Fraunhofer lines. So they started seeing that the sun is made up of the same material that we have here on Earth, which is pretty exciting. However, this is pretty exciting for them at the time. So during a solar eclipse in 1868 in India, a French astronomer, and it's this French-looking guy right there, his name is Jules Janssen, detected a bright yellow line at 587.49 nanometers in the solar chromosphere. So the solar chromosphere, for those who may not know, so when you look at the sun, you're seeing what's called the photosphere. The photosphere is hotter than the chromosphere. Now the chromosphere, you'll see that when you have a total solar eclipse. You'll also see the chromosphere when you're using what's called a hydrogen alpha telescope. So he took the spectra of the chromosphere. By the way, the chromosphere is the outermost region of the sun. The photosphere is underneath it. The photosphere is so bright it outshines the chromosphere. But he noticed that there's these lines. So there's this guy here, Luigi Palmieri, discovered this same line analyzing material sublimated during a recent eruption of Mount Vesuvius. It took Scottish chemist Sir William Ramsay to isolate the element from a mineral called cleveite. Cleveite is a mineral that contains some uraninite, some uranium, and things like that. And so there's a reason why that's important. Helium, so a radioactive element can emit alpha particles. When those alpha particles, which are helium nuclei, when it escapes after about maybe an inch, it will gather up electrons and become helium. So that's how he was able to discover the helium using this, this mineral, because alpha particles are helium nuclei without electrons. And then when they gather electrons from the atmosphere, they become helium. So that's how he was able to discover that. So, thanks to spectroscopy, helium was the first element discovered using spectroscopy. So that's kind of exciting. Okay, so now that we started understanding that elements have these spectral fingerprints, we started seeing that the sun has these these spectral fingerprints as absorption lines. So stellar spectroscopy started to accelerate in the latter half of the 19th century. Several astronomers started taking and cataloging these spectra. Early efforts was from this person right here, Angelo Secchi. I need to speak like an Italian. He's an Italian Catholic priest, and he started coming up with his own categorization or classifications of stars. Then Henry Draper, in the late 19th century, who some consider the pioneer of astrophotography, he began photographing these stellar spectra. And this became part of what is known as the Henry Draper catalog. So when you look at a star chart and you see HD 1, 2, 3, 4, 5, 6, it's based on that catalog by Henry Draper, which I didn't know. This is the part about researching for this stuff that it's exciting. You're like, oh, so that's where that came from. So the Henry Draper catalog gathered spectra from 225,300 different stars. So Now let's talk about my favorite subject, the Harvard computers. No, these weren't big computers in the basement. These were a group of women who started cataloging all of this spectra. The Harvard University started taking more photographs. They created an observatory down in Peru, set up an observatory there to start cataloging stellar spectra from other stars that they couldn't see up in Cambridge. Some of the notable computers are Williamina Fleming, originally from Scotland, Antonia Mari. Now, the interesting thing about her is a lot of the extra things, like when you look at the stellar classifications, they have little notations. She came up with a lot of those. Henrietta Swan-Leavitt. Has anyone heard of the period luminosity rule? She discovered the relationship between the luminosity and a period of Cepheid variables. And then Annie Jump Cannon, she is the one that is credited of coming up with the stellar system that we use today, OBAFGKM. So, by the way, these Harvard computers, they're like some of my heroes. But I want to talk about this person because she's like the big hero for me. Cecilia Payne Gaposchkin. She is the one that started, and she's originally from Great Britain. She used this data to establish that stars are mostly made of hydrogen and helium. A lot of scientists at the time thought that stars had the same junk we got, right? In fact, in her paper, she started saying, this is probably an error, but this is what I observed. Let's see, make sure I don't, okay. So her seminal work, or her dissertation, or thesis, I always get that wrong. It's called Stellar Atmospheres, and you can get this for free. So, a quick side note, I was going to go into astronomy, and I was going to go study stellar evolution, because I don't know what it is about stars, but I think it's fascinating. Her paper is really what started us on. And she worked at or studied at the Cavendish Institute in England. And the Cavendish Institute was one of the premier institutes that dealt with quantum mechanics. So she had that quantum mechanics background, and she came over into Harvard and started using that. And using that knowledge, she was able to understand how stars are made up and the ratios of things and how that stellar evolution came about. So she's like one of my big heroes. I just finished reading this book. I highly recommend it. This was part of my research for this. It's called The Glass Universe by Dava Sobel. By the way, Dava Sobel is an excellent author. She has written several books like Longitude, The Planets, and other things that kind of piqued my interest. So if you want, and I learned a lot of this stuff about the Harvard computers and Edward Pickerington, the Harvard Observatory, etc., from her book called The Glass Universe. Highly recommend it. All right, so let's start talking about stellar spectra. Okay, we're getting there, guys. So, as I mentioned earlier, most of us are probably familiar with the stellar classifications, O, B, A, F, G, K, M. The only reason I can remember that is from the mnemonic. O, be a fine girl or guy, kiss me. So, each class of stars, now this is a broad category of stars. There are variations and notations that make the spectra a little different. But we're only going to concentrate, especially if we're going to do spectra with our SeeStars, our smart telescopes, we're going to concentrate on the different types of classifications. So O, that is our hottest types of stars, right? There's not a whole bunch of them because they don't last very long. O-type stars are the hottest. Their temperature is greater than 30,000 degrees Kelvin. They have weak hydrogen, strong ionized helium, and highly ionized metal lines. And you'll see some of that, you won't see a lot of that here, but one of the things I want to show you, you'll notice how this goes towards the blue or the violet, and then down here it goes towards the red. Now, the peak of this output is towards the violet, into the ultraviolet. So we're only going to be able to see what's in the visible spectrum, but it emits a lot of light in the ultraviolet, those O-type stars. Likewise, M-type stars emit a lot in the infrared. So we'll go through each one of these. So blue-white, which is B, 10,000 to 30,000 Kelvin. They have strong neutral helium and moderate hydrogen lines. A, 7,500 to 10,000 Kelvin. It has the strongest Balmer, or hydrogen, also known as Balmer lines, and weak ionized calcium. Right here, you'll see some of that in the spectrum here. Yellow-white. It's weakening hydrogen. You'll see how these lines like get pronounced and then they start disappearing, and like you'll see lines up here start happening. It's an interesting thing to think about when we get into this. Yellow, like our sun, this is very similar to our sun. Weak hydrogen, strong ionized calcium and metal lines. Don't worry about what each one of these lines, just go along with me here. We're getting warmer here, cooler. K-type stars, you'll see a very dominant line in this, and I forget which one that is, but all of these lines here are the metallic lines. It's the heavier elements. And then, of course, the coolest red stars, they have strong neutral metal lines and molecular bands, specifically titanium dioxide. So this kind of gives you what all of these different spectra of the different classifications of stars. Now, one of the things I didn't put in the slide are Wolf-Rayet stars, and there's a special interest in those because they have some strong emission lines that you can look. All right. Remember I said it's cheap, right? We don't want to spend a lot of money on this stuff. So what you want, now this is, and I have some examples over here, you can use like a 27 lines per millimeter metal mesh, and they're not expensive. I bought like a couple sheets of it, and it wasn't very expensive at all. You can use a metal mesh. You can use cheap, and you can get them. I just ordered some on Amazon today. 50 or 100 lines per millimeter unblazed plastic diffraction film. You can get that from AliExpress. I bought it from Amazon, which is probably coming from AliExpress. Star Analyzer, that company that made that periodic table of all the different spectral lines of the elements, they make something called a Star Analyzer 100, and they also have a 200. The thing with the Star Analyzers, when you have more lines, and the reason why is because you have to attach it in front of the telescope. You have to have a low lines per millimeter count because the spectrum won't show up on the chip. The Star Analyzer 100 and 200 are designed to be like attached to a filter wheel that's closer to the chip, and you'll be able to get that spectra. Now, there is a way that you can use it by doing something called spectrum stitching, where you take a spectra and you move the telescope, you get the next part, move the telescope, but it's a pain in the rear. So that's what you could do with the Star Analyzer. And it's just a filter that has a diffraction grating on it. Now, you need a way to attach this grating to your SeeStar. There's a couple ways to do it. One, just use good old tape. It's important. You want to make sure that you're not covering the entire opening with the diffraction grating. The reason why is plate solving won't work very well unless you have bright stars. What you could do is just put it in like part of the field and you'll be able to get the plate solving to work. So like for example, right here, the entire diffraction grating is all around, is covering up the main objective. Now the SeeStar, and I don't remember if the SeeStar S30 uses the wide angle to help do plate solving. But when I tried it, it didn't do a good job plate solving. So when you zoom in or slew to a particular object, it won't plate solve very well. Carl Jung, or Jung, I don't know if I'm saying that right. He sells this adapter in both for the S30 and also the S50. And I brought a couple examples. It's about $40, I think, for both of them. I don't remember. But if you email him and he gives you your PayPal account, he'll ship this to you with the wire mesh. Now, to analyze it, you can use two pieces of software that I've seen. RSpec is what I use. That company that makes the star analyzer sells this. I think it's like $75. And this software allows you to look at the spectra after you calibrate it and find all the absorption lines. There's something called BASS. It's made from an astronomical society in Britain. And it's for free, and you can download it. And I've used both, but I find RSpec a little better. Now, this isn't spectra that I've done. Kazuyashi and Mamura made these with one of those cheap unblazed diffraction grating sheets. And he 3D, I think he's the one that actually, that picture, whoops. This picture here, this is how he did that spectra, is by taping this onto the front of the SeeStar. But you'll start to see some of the absorption lines in Sirius here? See them? You get down into Betelgeuse, you see a lot more, and it's towards the red, right? You're not going to get like high resolution, but you will be able to see some of those broader lines. The other thing that you can do with spectroscopy, if you had a nicer setup, is, for example, I don't know if, well, I have it on mine. So Regulus is an example of a star that rotates very fast. In fact, it rotates so much it's more football shaped than a sphere. What they can do with spectroscopy, if you see those absorption lines but they're wide, that means that the star is rotating quickly. I don't think you're going to get that kind of resolution, but you may see those things more pronounced on a star like Regulus. But as you can see here, like with Rigel, which is a type B star, you'll see that it's shifted more towards the blue and ultraviolet. And then as you start going down, you start seeing the spectrum shift towards the right. But you will see some of these lines in the software that you use to analyze it can actually show you what each one of those lines are. So things to remember when you're doing spectroscopy using this method with your SeeStars. You want to focus on the spectrum itself and not the star. The reason why is because the spectrum is not, it comes off at an angle, so you want to focus on the spectra itself and not the star. What I usually do, since the SeeStar has, the chip is, and I hate this, the chip is up and down like this, it's not left to right. I use the uppermost, oh, I didn't have a picture of that. So when you look at a star, when you're doing this, you'll see like a plus sign, and you'll see a couple fainter lines. I use the top or the bottom spectra, and then I rotate it when I use the software to analyze it. So you'll need to use manual focus. You can autofocus on the star itself and then adjust the focus to where you get the sharpest spectra. It will cause the star to go out of focus.
Are you talking like with a Batnoff mask?
Oh, no. So the SeeStar and also the dwarf, and you could apply these same principles to a dwarf telescope. It's not just the SeeStar. SeeStar and the dwarf has autofocus. And so you could say focus on the star and it'll get to the focus, but then you can go into manual focus mode and adjust it to where you see, because the spectra will be a little dispersed, but as you adjust it, the star will start going out of focus, but the spectra starts coming in. A Batnoff mask would not work really well, because think about it, like a Batnoff mask, when you're seeing the star, you'll see that it distorts, you'll see some refraction colors and stuff in the lines. So you couldn't do that because the Batnoff mask is assuming a point source, spectra is not. Okay, also, I don't have the software working yet on this laptop. Calibration when you're doing spectra, you want to have the star itself in the spectra, and that's where you say, okay, that's my 0 point for this spectra. And then you identify known like a hydrogen alpha line or a hydrogen beta line, and then you line up the hydrogen beta line in the software to that, and then the rest of the spectra is calibrated. And I'll show you in this next picture. So here's a picture of Arcturus that I took last year. So here's the star. You can see how the star is slightly out of focus, but the spectra itself is actually doing pretty good. And I don't know if this really shows you, but there are some gaps in the lines. And you'll see here, the star itself is the 0 point. You see the 0 point? And as you go across, I lined it up with, I believe, the hydrogen beta line here. And so the hydrogen beta line, I was able to say, that's the hydrogen beta line. And then the rest of the stuff started showing up. And our spec allows you to show, well, I want to see these lines, and it'll apply those lines on top of the spectra so that you can actually see if they line up. Down here is a rendering of the interpretation of this spectra. So taking this data, it's saying, okay, based on this information, it's essentially creating a simulation based on the data of the spectra of Arcturus. So you'll see some of these, like these gaps here, like here, what is that? Here's the sodium line right here. So you see a sodium line. Let's see, what's this one here? Here's the other hydrogen, this is the hydrogen alpha line, and you'll see a little dip, these little dips. You know, there's the hydrogen beta line. So the next one is Regulus. So Regulus is an interesting star, and I forget what class that is. I think it's an A class star. You'll see here, we have some, our carbon-2 line. We have our hydrogen beta line, and you'll see right here, I don't know if you can see it that well, there's a real big dip there, hydrogen beta line. And then over here we have our hydrogen alpha line. Now, are you going to get all of the fine little lines, all the Fraunhofer lines or whatever? No. You really need to get like a slit spectroscope. And you can get one of those for your telescope for about $1,200, $1,300. That will give you the resolution that you would need to see all those other lines. So this is Regulus, this is the spectra, and you can see some of those. Now, I was using that metal mesh. It's the cheapest way to do this. Well, one of the cheapest. It's like $1 for a little piece. But anyway, so this allows you to see some of this coarse spectra, so you can see some of those broad lines. So, future plans of mine. So I want to chuck the wire mesh model, and I want to get a 50 line per minute cheap grating. So I just bought from Amazon, it was $20 for 2 of them. I got a 50 line and an 80 line. One of the things with the 80 line, you'll have to go, and this is exactly what he did here. When you take a picture of, like, say, Regulus, and he goes up, since it's the longest axis going up and down, he gets the Regulus in the center, and then he moves it up until he starts to see the spectrum appear. Then he does his focusing, then takes the picture. You can take like multiple pictures and stack them manually. The SeeStar app will not stack these things really well, but I'm going to tell you a way around that here in a second. I can't wait for these things. I've been looking forward to doing this. Because what I want to do is, I'm calling it the Hissong Stellar Catalog. I want to go through all the bright stars in the sky, take pictures of them, and gather their spectra and put it in like one big sheet. Just so that I can see how all the different lines line up. Yeah, the catalog bright stars, that's the thing I want to do. All right. I really wanted to kind of show a demonstration tonight, but Ohio clouds prevented that. But I do have both of those devices I was telling you about on display here, so you can take a look at them. Now, this is something that Kai, and by the way, Kai is like really well known in the Smart Telescope community. He runs the Smart Telescope Underground Facebook group. A lot of people on that group are learning how to do things and experimenting. And so if you're interested in doing anything more than just take pretty pictures, look at that Facebook group. It's called Smart Telescope Underground, and Kai runs that, and he is brilliant. But he, like I said, he sells those. You just email him, and then he'll send you those. He's pretty quick about it too. I plan to do some designs myself, 3D print them, and I will be providing that on Thingiverse if anybody else wants to 3D print it. So, I've been using the SeeStar now for a year and a half, 2 years. I want to give you some updates. Photometry. I am a variable star observer. I love variable stars. Some of my heroes are variable star observers, like Leslie Peltier. I've been now doing photometry that's been reliable using the SeeStar. I am planning to do, well, I am doing a talk in May about how I go about doing photometry with it. I'm also going to be writing a series of articles about doing photometry and also stellar spectroscopy for the prime focus, so you won't want to miss those. So using a program that's not free, a program called Tycho Tracker, you can do photometry. Also, you can do astrometry by tracking asteroids and discovering things like that using Tycho Tracker and the SeeStar. Here's an example of, I think this is our Leo. So I submitted my observation. There it is. My observer code is HJS. You can get an observer code for free from the AAVSO. But I was so proud to see, there's my little star estimate. Of course, I did a bunch of others. Here's all the other ones that I did. The cool thing about this, and I'm going to talk about this in just a second. If you have a catalog of variable stars, you can go set up the SeeStar, go take all those pictures, reduce them, send them off to the AAVSO. It's a fun way to do citizen science and learn more about the universe. And you can learn things about the luminosity period rule. Maybe I'm saying it wrong. This is the next thing I wanted to show you. There's a piece of software out there called NINA, and I don't remember what it stands for. But this software, what is it?
Nighttime imaging and astronomy.
Thanks, Charles. Appreciate that. So NINA is what they use for big rigs to control, the mount, the camera, the focuser, the filter wheel, and a bunch of other things. Well, recently, and they didn't really advertise this, CWO came out with alpaca drivers that allows NINA to control the SeeStar. This is a game changer. I can now take my own darks, because the way SeeStars work is they automatically take the darks, and you can also do flats, but it's their flat thing that they do. But with NINA, I can take as many darks as I want, I can take as many flats as I want, and take the flats with the different filters. And it has allowed me more control over processing than I ever did using the app to take care of the pre-processing stuff. So the things that you can control, you can, So it supports slewing, plate solving, autofocusing, what filter you're using, all in on your computer. So you don't have to use your phone app anymore to do it. This picture I took Thursday night. No, it was last night, I think, of the Orion Nebula. I had much more ability to control the noise. So what I did is I took 20, 30-second dark frames, because I think the SeeStar will take like 3 or 4. The more dark frames you take, and also if you take some bias frames, the better off your processing is going to be and the better off your data. I also did my own flats, And I have an example of my flat field box that I sell. In fact, I have a customer in here right now. But it allows for much better processing, and importantly, it allows for much better data if you're going to do things like photometry. So anyway, let's see. And that's it. So thanks, everyone. If anybody has questions, yeah, okay. By the way, ChatGPT did that. All right, everybody look at the ceiling. I had a teacher that would do that when we watch a film. He'd go, look at the ceiling, and all of us idiots would go, huh? And turn the lights on. So, yeah, go ahead, Art.
Question.
Yeah.
Color photography really wasn't anything more than experimental in the 18th century.
Yeah.
And the time frame when they first developed the spectroscope, visually you could see the colors, but a photographic image in a color format wasn't available until the 20th century in a commercial basis.
Yeah.
How did were they looking for the darks?
Yeah, so they knew the frequency. So it's based on, they knew what kind of, because they would use slits, right? They would know the dispersion of that slit, and then they would see those lines. And because they understood, oh, that's a pretty prominent line in this area of the spectrum, they're able to say, okay, when they can calibrate by looking at known lines, and using that calibration, they were able to determine the rest of the spectra. So you don't need a color in fact, I would prefer to do spectra with a monochrome camera. I don't care about the colors. I just care about the lines in there. And as soon as you know where a particular line is, you can do that. Color spectra just makes it look prettier. But yeah, so when they started doing, Henry Draper, it's a really cool story about him and his wife. Henry Draper started experimenting with photography, and he built his own observatory, and I forget if it was in Long Island or if it was up in Massachusetts, I forget. He started taking pictures of stars, and then when he discovered that people were doing, or they knew about spectroscopy then, but all that was done by eye. So he started experimenting by taking plates of the spectra. It's actually really interesting. They went to a solar eclipse, I believe it was in Colorado. So his wife, and I forget her name, but his wife and him went to a solar eclipse. Of course, she didn't get to see the solar eclipse because she's counting down the numbers. We didn't have smartphones back then. It says 5, 4. She's counting down the time so that all the other people can get to see it. Well, he got sick and died early, and he already had his catalog and his plates. So his wife, man, I really wish I remember her name. His wife contacted Pickering, Edward Pickering, I think that's his name, at Harvard Observatory, and wanted to continue his legacy. So what they did at the Harvard Observatory was continue doing the spectra and cataloging it. And it became this huge thing where the Henry Draper catalog was started to preserve his memory of what he was doing. So it's a great story. I highly recommend reading this book. If you're into history, especially history of science, it's perfect. So.
It was Mary Anna Draper.
Mary what?
Mary Anna Draper.
Okay, that's right. Yeah, Mary Anna Draper. Thank you. Yeah, go ahead.
In one of your slides, you showed the classification of the stars by temperature, right? Mm-hmm. How is that information deduced or obtained?
Okay, so based on the, so there's a couple things, and I might get this wrong. I'm trying to remember it correctly. So first of all, the classifications of the stars is based on temperature. Okay, but they did see a correlation. There we go. They did see a correlation of some of the absorption lines based on the characteristics of what was known about that star, right? As far as temperature is concerned, the hotter something is, the more it emits radiation towards the higher frequencies, okay? The more energetic something is, it's going to emit higher frequencies. So if you look at an O-type star, you'll see that the spectra skews towards the violet. In fact, O-type stars really emit a lot of radiation in the ultraviolet. As you get cooler, and they knew this from understanding, and I get this wrong all the time, like black body radiation, how much, like we radiate infrared, right? So we're not hot enough to radiate up towards, higher frequencies, thank goodness. In fact, one of the things I've gotten into is gamma ray spectroscopy, which shows you how you can identify various radioactive isotopes. That's been pretty cool too. So they're able to identify if something by temperature, by where it is in the spectra. So that's how and then because they were able to identify things that are hotter go more towards the ultraviolet, less into the infrared, they started noticing that these certain lines are showing up in a consistent manner. So there is a correlation between the temperature of the star and the absorption lines that show up. So, hope I answered your question. Any other questions? All right. Yeah.
So, you can take the signature of the star, but wouldn't that change over the life of the star?
Yes, the spectrum does change.
It wouldn't be like the periodic table, but that would be consistent forever.
Yeah, so in stellar evolution, the thing that happens when stars evolve, right, is it's converting the effusion, hydrogen into helium, helium into like carbon, oxygen, lithium, and then it keeps going up. There's only a certain point that it can go, and that's iron. And then like our sun will never get to the point of fusing iron. It's just not massive enough. But it will be doing things like oxygen and carbon and neon and of course helium, and there's some other things, calcium, and sodium. As it's using up its fuel, it starts fusing inside the core other elements into heavier elements, and it keeps doing that. Well, eventually that gets mixed up into the atmosphere of the star or our sun, and you'll start seeing these absorption lines. It's really saying, if you start seeing these absorption lines, so like early in a star's life, you'll have a lot less of those, they call it metals, right? Anything heavier than helium. As the star ages, it's churning up and fusing more of these other elements like the oxygen and all that. And that starts getting inside the atmosphere of the star, and that starts absorbing that area of light. Now, in like Wolf-Rayet stars, there are some cases where it has emission lines. Like you won't see a lot of emission lines in stellar spectra, but Wolf-Rayet stars, and there may be some other ones, do have an emission line that is seen. So what a lot of folks that do this, they like finding the Wolf-Rayet stars so they can see that emission line, which is kind of neat. And I forget where that is. But yeah, as the star evolves, these other elements start turning up into the stellar atmosphere, and it starts absorbing that light, and those lines start, just like if you look here, there's a lot more metal lines in an M-class star, because either an M-class star is later in its life, or if it started its life with not a lot of mass, it's an M-class star for the rest of its life, and it'll live for quadrillions of years.
So you wouldn't be able to tell, you really couldn't use that analysis to really age the star, because it might already start at the low spectrum.
So there are ways, and you're kind of stretching what I understand. There are ways to understand if a particular star, so there are M-class stars that are dwarf stars, right? And they understand that because of that period luminosity rule. What that means is there's a correlation between the period of the star pulsating and brightening and dimming and the wattage of the star. if they see that it has a certain curve, like a dwarf star might have, because that period luminosity, as soon as you know how, like how much power it's the sun, the luminosity of that particular star, you can deduce the size of it, right? So when you have a red giant star, like if it's going in from a K or an M type star like Betelgeuse, because it pulsates at a certain frequency, they can determine the mass from its luminosity. It's like, wow, it's pulsating this slowly or fast. It must be a huge star because it's very luminous. And that's my story, and I'm sticking to it. All right, anything else? All right, well, thank you very much, everyone. I'll bring up my funny picture of myself. If you want to take a look at any of the things over there, ask me questions about the SeeStar or anything like that. I am willing to answer questions. So.